Hey, what's up, my chemistry people? Are we ready for another free response? I know I've been waiting all day for this. One fission reaction for uranium-235 is represented by the nuclear equation below. Both radioisotopes produced by this fission reaction undergo beta decay. Part A. Balance the fission reaction for uranium-235 by placing the appropriate values in the empty boxes in the equation above. Alright, let's start with this empty box here. Remember, the sum of the numbers on the bottom, on the left-hand side of the equation, has to equal the sum of the numbers on the bottom on the right-hand side of the equation. So since we have all of the numbers on the bottom on the right-hand side, let's just sum those together. 54 plus 38 is 92. So what number plus 0 equals 92? You guessed it, 92. All right, let's hit this box. Same thing applies, except now we're focused on the numbers at the top. On the left-hand side of the equation, 235 plus 1, I don't even need a calculator for this, it's 236. On the right-hand side of the equation, be careful. We have 94, but then we have 2 of these neutrons. It's basically like saying this. So, our total, 236, minus our 94, enter, minus 1, enter, minus 1 again, gives me 140 as the mass of this isotope of xenon. Boom! 2 easy points right there. Part B. Explain, in terms of both reactants and products, why the reaction represented by the nuclear equation is a fission reaction. Alright, a couple different ways you can go here. Okay, now you don't have to write this verbatim or word for word, but you do have to get this general idea of fission expressed. So, the uranium-235 nucleus splits into 2 smaller nuclei. So again, the key here is simply to recognize that fission is this idea of splitting a large nucleus into 2 smaller ones, or more smaller ones, splitting it. Part C, consider the nuclear decay of strontium-94. Subpart I, calculate the number of neutrons and electrons in a neutral atom of strontium-94. I'm gonna head to my trusty periodic table for this. I'm gonna zoom in on my good friend strontium. It has atomic number 38. I'm going to rewrite my nucleide symbol to help me remember my atomic number of 38. Now we're talking about a neutral atom here. So number of electrons equals number of protons. Number of protons is equal to the atomic number. So we've got 38 electrons because my atomic number is 38, which tells me the number of protons, and in a neutral atom will also tell me my number of electrons. Boom for 1 point. Number of neutrons is equal to our mass number minus the atomic number. Remember, the mass number is your protons and your neutrons, and your atomic number is just your number of protons. So my mass number is 94 minus 38. I'm gonna make a quick jump to my calculator because I've got it. 56 neutrons. Boom. Second point. Write the balanced equation for the nuclear decay of strontium-94. My goodness, is this alpha decay? Is it beta decay? Should I just choose? Remember, free response. Many times, it's asking you to think about early parts of the problem. Did you read? Are you carrying those parts from the past down here to the present? As I scroll back up here, we're reminded that both radioisotopes produced by this fission reaction undergo beta decay. Strontium-94 is one of those radioisotopes. So I'm going to rewrite the nucleide symbol for strontium-94. It's a decay equation. So this is the only thing that I'm going to have on the left-hand side of my equation. It decays by beta emission or beta decay, which is essentially an electron, 0 mass, -1 charge. What forms then after strontium emits a beta particle? Well, the mass is going to remain unchanged. Because remember, those electrons or beta particles that are emitted essentially have 0 mass. However, a neutron has turned into a proton. What number plus -1 equals 38? Answer, 39. Now, if the atomic number has changed, if the number of protons has changed, it's no longer an atom of strontium. Where could I go to figure out what atom it has turned into? Periodic table. Good old yttrium. Boom. 2 points. Subpart I. Explain, in terms of protons and neutrons, why strontium-94 and the product of its nuclear decay are not considered isotopes of strontium. why is this and this not considered isotopes? Now, it's important that you read this carefully. You have to explain in terms of protons and neutrons. So let's do it in terms of protons first. We'll say strontium-94 has 38 protons, while yttrium-94 has 39 protons, making them different elements. Remember, it's the number of protons that we use to identify an element. Strontium-94 has 56 neutrons, while yttrium-94 has 55 neutrons. So, although they have the same mass, they have different numbers of protons, making them different elements and not isotopes of strontium. All right, and that takes us to our final subsection here. On the diagram below, draw an arrow to represent the path of an emitted beta particle in the electric field between two oppositely charged metal plates. So as you take a look, we have a sample of strontium-94, and it's undergoing beta decay. It's giving off beta particles, and we want to know if those beta particles are emitted through an electric field between two oppositely charged plates. We have a positively charged plate and a negatively charged plate. What path would that beta particle take? Well, you have to remember that beta particles are essentially electrons. They have a negative charge. And so beta particles, or negative charges, are going to be repelled from like charges or other negatively charged things and attracted to positively charged things. So if I were to draw the path of a beta particle, I would draw it repelled from the negatively charged plate and attracted to the positively charged plate. Free response, done.